Arman, hold on. Good morning, everyone. Welcome back to the second day of the Chennai Symposium. We will have two talks in the morning session. The chair for the morning session is Dr. Sumanta Chakrabarti from IACS Kolkata. Over to you, Sumanta.
Yeah, thank you, Sriram. So it's nice to see the second symposium going on. I had been there in the first symposium, so I wish this happens repeatedly. Now let us get started with today's lecture. So good morning. And today's first speaker is Professor Arman Shafieloo, and he will talk about status of the standard model of cosmology. So Professor Arman, it's up to you now. Please go ahead.
Okay, thank you very much. Okay, so first of all, good morning, everyone. And I would like first to thank Sriram and other organizers for inviting me to this very interesting symposium. And it is also great to see many of the good old friends and colleagues. And I can see them. And then yesterday I was listening to the talks. So it feels really good. I haven't been to India now, it's for more than 11 years. And I wish to visit India in 2020, which then the pandemic happens and now God knows what would happen. But anyway, it's good to see you virtually here. And yeah, and I hope to see many of you in person, hopefully in this year. Okay, so I'm going to talk about the status of the standard model of cosmology and basically some background first, and then I try to discuss a little bit about the tensions and about some of the solutions, and then what the prospects in the near future. So the era of precision cosmology practically in last 20-30 years, by combining theoretical works with many measurements and advanced statistical techniques, we could practically put sharp constraints on the parameters of the different cosmological models which we had. And among which we had the standard model of cosmology, which is a flat FLRW universe where we assume dark energy is cosmological constant and dark matter is cold, and we have a power law from our premodel spectrum, and practically we can describe this universe by only 6 parameters. So it's a nice model, and you know, phenomenologically it is it's simple, and it is basically has a very good support from many different observations. But we should realize that the standard model of cosmology is practically a combination of assumptions. I mean, the fact that we assume dark energy because for a constant, or power law premodel spectrum, or even FLRW or flatness, these are all assumptions which are based on really good support observationally, but still they are assumptions. So this is something that I will come back to it later. So what is the status of this model in 2022? It's now about 24, 25 years after the discovery of the acceleration of the universe by type 1a supernova. Of course, there were hints of something wrong with the SCAD model from the large-scale structure data, but some of the most important confirmation comes from the supernova type 1a's, which at that time two groups realized that, okay, we have acceleration in the expansion history in the late universe, and we need dark energy, and now time passed. Now we have these compilations with more than 1,000 type 1a's, and when we look at the residuals, we realize that yes, this model works pretty well. We have then cosmological background. Again, 20 years ago, we barely had the first acoustic peak. When we look at the data from the maxima or boomerang, before WMAP, we barely had the first acoustic peak, but now by the Planck satellite, we can go to the 4th, 5th, or even 6th peak. And again, when we look at the residuals, we see that the standard model basically fit this data very well up to very high multiples. Situation is also good in the case of the large structure data. These are some plots from the latest release data from the Sloan Digital Sky Survey and EBOS collaboration, which I was involved, and yeah, I mean, again, the standard model seems to fit the gross data as well as the expansion history data from the baryon acoustic oscillation very well. So SDSS 4 was practically, we could generate the largest 3D map of the universe ever created, which was very nice. And but again, the standard model was doing pretty well in this context. So a standard model of cosmology is certainly a reasonable model, and it's a combination of reasonable assumptions. But this has not been all, and as we all know, there have been some persistent tensions in this model. In fact, everything started in 2013 with the first release of the Planck data, where with the first release, they come up and said, okay, when we feed the standard model to the CMB data, we get Hubble parameter of about 67, 68, which was at that time in some tension with the local measurements from the Cepheids and the supernova. And there were hopes that, there might be some tensions in some of the data, but nothing really disappeared. And in 2020, 2021, now what we have is more than 4 sigma tensions. This is from one of the latest results from the Shoes collaboration. There's even more recent results than this, but the tension remained at more than 4 sigma. So practically, when we observe, when we calculate, measure the Hubble constant at the very low redshifts by calibrating Cepheids and the local supernova, we get the Hubble parameter close to 73, 74. And when we feed the standard model to CMB data, then the constraints on the posterior and the Hubble parameter ends up to be something about 67 with a very tiny error bar. So this is something which is known as the Hubble tension, as we all know, and this has been there and remained there. But here I would like to also say that it's not only about the H0 and CMB, as there have been some other inconsistencies going on. For example, when the weak lensing surveys like CFHT lens or the kids, they come up with their measurements of the sigma 8 omega matter, assuming the standard model, the constraints which they get on the omega matter sigma 8 was again not very well matched with the constraints which we could get from the CMB. Another issue was that when we were looking at the omega matter H square, which is somehow observable from the both CMB and baryon acoustic oscillation, we could see still there is a particular tension between the expectation of the cosmological background and what we have from the Lyman alpha baryon acoustic oscillation. For example, here in this left plot, we see that when we consider Pantone data and all baryon acoustic oscillation data, we get this dark, black PDF. And when we add Lyman alpha, then basically it's shifted to the lower values. And when we add CMB, basically it's shifted to the higher values. And so this has been another tension which has been there. And we could basically associate it with some, lower expansion history, which we observed from the baryon acoustic oscillation in the Lyman alpha forest. So there have been these tensions which have been having different faces. And then, if we add curvature, things become even more interesting and complicated, as there was this paper by Di Valentino, Melchiori, and Silk, which they showed that, if you basically allow curvature in the basically pipeline of the CMB analysis, then we realized that, okay, things even become worse. And it was basically in the Planck papers, it was basically a paragraph about that. But further and more detailed analysis highlighted this fact that yes, in fact, if we allow curvature, CMB pushed the standard model to a higher value of a matter density. So these tensions have been there, which is not just the Hubble tension, and we are facing a kind of a multi-phase problem. So how to go beyond this vanilla model and this standard model? Well, I can categorize things in a few main categories. One is about finding features or deviations in the data beyond the flexibility of the standard model, which we can use non-parametric or model-independent reconstructions. These are good because we might find features that data suggest and or model cannot really explain. And that can be used to falsify and then says, okay, there's some issues with the model. Another approach can be the falsification using litmus tests, basically saying yes, assuming a hypothesis, trying to focus the power of the data to say yes, no answer to a particular assumption. Again, interesting. I will come back to it in a few slides. And one of the most trivial ways is that to finding tensions among different independent data, assuming the particular model. So this is very good to understand that if assuming a particular model, if different data are in a mutual consistency or not. And at the same time, it can help us to understand if there's a systematic or not. And if there is no systematic, then we can say, okay, then the model is not really capable to explain the different data pretty well. So now introducing, and basically from the theoretical side or phenomenological side, of course, if we can come up with the models that can explain the data better, then that would be a great achievement. But this requires to be, statistically significant, which is not an easy task to do, because a standard model is very, very simple phenomenologically. It has just 6 parameters. And when we talk about significantly better statistically, we usually talk about the Bayesian evidence, which is very sensitive to the degrees of freedom. And so usually when we have models with more degrees of freedom, even when we have better likelihood associated with the chi-square or reduced chi-square, still, standard model can be a winner because it has lower degrees of freedom. So when we deal or we come up with, introducing new theoretical or phenomenological models, we have to consider that they need to be better than the standard model. So these are the ways, these basically the highways to go beyond the standard model. And I just try to explain some of these attempts, for example, about the falsification. This is a work which we did with Varun Sani and Alexei Starobinsky. It's already 7-8 years ago. Time really flies. And it was with the first release of the SDSS quasar BAO data, which we realized that if we come up with a form of or Ohm diagnostic, and we basically use the observables of the BAO, we realized that we can come up with this simple form we call Ohm H square, which we could compare the observables of the CMB and baryon acoustic oscillation. And at that time, we found between 2 to 3 sigma tension between observables of the BAO and CMB. And at that time, we basically tried to emphasize that we see this tension, but it should be most probably associated with the systematics. But I would say that these things didn't really disappear. With the latest release of the baryon acoustic oscillation from the SDSS, results didn't change much. The tensions now are not at the level of more than 2 sigma, but it's at the edge of the 2 sigma. So we need really further observations to understand what is really going on. Another approach which I explained was about comparing different data assuming a particular model. So there was this comprehensive paper which me and one of my postdocs at that time, Benjamin Louis, we collaborated with the SDSS collaboration, SDSS3 at that time in this Nature Astronomy paper, which we tried to use KL divergence to quantify the degree of tension when we assume a model and then when you consider multiple combination of different data. And the result was interesting because we found 2 important tensions, and one was in fact with the Hubble parameter, and another one was in fact with the Lyman alpha. And so it was basically somehow confirming that these tensions are there and are practically pretty significant in the case of the standard model. And again, things really didn't change much for the case of the Lyman alpha BAO, as well as things for the case of the Hubble constant measurements become even worse. As I said, by the latest observations from the Shoes collaboration, the tension even increased. The mean value didn't change much, but their uncertainties shrink, so the level of tension practically increased by time. Okay, so we have practically multiple suspects. It's like that. Something is wrong, but we don't know where it is and what it is. And there are many possibilities. It's not like that. We just blame local observation of the Hubble constant. As I said, there are tensions in other things too, in weak lensing shear, in the Lyman alpha from the BAO, and curvature when we assume curvature. So it's very complicated to understand what is really going on, and how to resolve that. Again, what people can say is that, okay, we can have statistical fluctuations, which probably not anymore, because now the tensions are at more than 4 sigma, and we cannot really associate it to the statistical fluctuations. It's not just few percent, it's just like a very, very tiny possibility. One big probability or possibility, which I personally am a big fan of it, is systematics in one or some of the data. So the logic or philosophy behind this mentality is that when we have some tensions in a model and we have some data, we expect that by some minimal modifications, we should be able to resolve majority of these tensions. But the reality is not this. The point is that it's very difficult with some minimal modification to the standard model. We resolve most of these tensions. And this basically come up to basically give us a hint that probably we have systematics in one or even some of the data. So we had this paper with Charlie Lee, my ex-postdoc, and Varun and Alexei a couple of years ago, which practically from the concept of the dark energy, we try to explain that it's really difficult to resolve the tensions by minimal modification in the dark energy sector, and we practically may suspect systematic in some of the data. Another approach which has been, loads of papers in the literature is about extended models or new physics, which is again good for theorists or people who work on phenomenology to come up. These are nice things to do. We are exploring all different possibilities, but we should also consider that in many of these solutions or many of these attempts, what has been done, in fact, has been by having more degrees of freedom in these models or extended models. And when you have more degrees of freedom, your confidence contours become inflated, become larger. And when you have larger confidence contours, these contours basically have a better overlap. And people usually call this alleviation of the tensions or reducing the tensions. So practically how we are reducing the tension is that you're adding some degrees of freedom. These degrees of freedom may not really change the behavior of the model. These degrees of freedom, mainly, they are just inflating the confidence contours. But having larger confidence contours, you have a better overlap between the contours. Hence, we can say that, okay, you are reducing the tension. It is okay to do that, it's fine, but I think there have been a huge amount of overselling in the literature in this regard, which I think is not appropriate. So we should realize that in so many of these cases, again, the tensions are reduced by larger contours, and not that this model, for example, prefers literally a larger value of Hubble parameter, or you have another way to reduce the tension physically. Okay, so I spend about a third of my time on this introduction. So I now try to explain a little bit about some of the potential possibilities, some of the approaches that we can have to the standard model to reduce the tensions. So these are the pillars of the standard model: flatness, isotropy, homogeneity, lambda dark energy, Pavlov model spectrum, and FLRW and dark matter. So I just try to discuss about two main pillars. One is about dark energy, and one is about P-model spectrum. So about the dark energy, see what we can do if we want to go beyond W equal to -1. So there have been two main attempts with different shapes. One has been early dark energy, mainly proposed by the Mark Kamnikovsky's group, where they basically, the logic was practically very simple, that the H0RD is practically a quantity that one can derive even by the low redshift observations, is anchoring the low redshift and the high redshift. Now we want high value of the H0. So if we want to have a higher value of H0 while keep the value of H0RD intact, the best way is that to have a lower value of RD. To have a lower value of RD, which is an early universe parameter, one best way is that to have a larger denominator in this equation. It's going from the last scattering surface to redshift of infinity. So to have a larger value of amount for this denominator, the best is to have a higher Hubble parameter. We cannot touch the matter density. What if we have some substantial amount of dark energy? Means that few percent in comparison to the matter density at that redshift, which is a redshift of 1,100. So comparing to the lambda, at that redshift, lambda is just 0. But you assume that we have some substantial amount of dark energy. Comparable means that it's not negligible with respect to the matter density or radiation, and that basically can increase the denominator. Having larger denominator will have a lower value of RD. Lower value of RD basically helps us with the H0, having larger value of H0. So this was the logic behind this work, and it basically works pretty well. But it works pretty well again, mainly because it didn't really shift the central value, but it mainly enlarged the contours, as we see here in some follow-up work by the Colin Hill, which basically says that no, these early dark energy models are not really resolving the tensions. And the point was that yes, when you look at the central value, combining many different data for this model, the central value shift from 67.3 to 68.3 with the larger error bar. So hence you have a lower tension. But in fact, it's not like that you are really shifting H0 to the substantially larger value. Of course, there are problems also with the perturbation issue, which is beyond this. But in practice, early dark energy models have not been really able to completely resolve the tension. So we attempt to solve the problem from another angle. I'm just a few minutes on this. And our strategy was that, okay, it's good time, good opportunity to kill lambda, and why not? It's a fun thing to do. And but one assumption was that let's assume that some of the data might have systematic. So we didn't try to have a model which satisfies all the data. But we try to have a model which satisfies some of the data, which are literally have a completely different kind of systematics. And we chose basically two data from two of the most experts groups, which are like a very, groups which are very content and, working together for many years. And one was CMB and one was from the shoes analysis. And we said, okay, let's come up with a model which can satisfy these two observations. And we try to target the near future and not now. So we said, okay, let's go with a model which may kill the lambda, not now, but in the future, if the current data is correct. And we try to have a very simple model, simple phenomenologically, that it doesn't have many degrees of freedom. So we come up with the concept of the PEDE, phenomenologically emergent dark energy, with the Shaolei, one of my ex-postdocs, which is a very simple model that dark energy doesn't exist in the past. It's philosophically simple, and dark energy basically emerges in the later time. And so the model, practically, we propose a model with no degree of freedom. It's just have a tangent hyperbolic equation, and we attempt to basically be a model which works better in the near future. So when we compare the lambda CDM and the CPL parameterization, we realize that with no H0 prior, basically means that if we have the current observation, the PEDE is not favored to the lambda CDM, and lambda CDM is better. But if we put some hard cut sharp priors on H0, basically means that H0 be, in its 97% possibility, then we realize that the PEDE is working much better than the lambda CDM. So what does it mean? It means that if in the near future, H0 really ends up to be close to 72, 73 with a smaller error bar, then this PEDE model can practically kill lambda with a very high confidence. So the model was practically well received. There have been many attempts, but for example, this is a work by the Holy Cow collaboration, which they compared some of the models, including our PEDE and the early dark energy model. And you see that the PEDE is one of the only models which by nature, it prefers a higher value of H0. So this has been the important things about the PEDE, that it generically needs a higher value of H0. And if it happens to be H0 to be 70 to 74, then those very small, the unique local measurements can be very much supportive of this model. The next attempt we had was basically to generalize this model and says, okay, PEDE and lambda CDM are two models, both fixed, and it's very difficult to compare them. Only we need to come up with some statistical model. Then we come with a by equation, a complicated model which is called the generalized emergent dark energy. But the fact is that this particular form can connect PEDE and LCDM and lambda, in a sense that, to a special limit of this delta parameter, it is only one parameter. When delta is equal to 0, it gives you lambda CDM model. As you see that if delta is equal to 0, this would be just -1. And when delta equal to 1, we come back to the PEDE. So we have one parametric form, one degree of freedom. And now if I fit it with different data, the posterior of this parameter can help us to understand the data is consistent with which data. So, and the model can have a very flexible behavior. There have been some work for the other groups also on that. And this is the results which we got for the GEDA when we fixed it, when we fit it with the CMB and R19 from the shoes. And we realized that, yes, in fact, the data prefers a delta larger than 0. So what does it mean? It means that the data practically prefers an emergent dark energy. It means that if at some times in the past, dark energy could have been emerged from nothing. And so time will show if this model works better or not. So we have also some, extended works, the full analysis, and including, and we see that in the delta for combination of many data is substantially better than the lambda CDM model. And as we see, delta equal to 0 is associated to the lambda, and or posterior and delta practically ruled out this model at more than 3 sigma. And also when we do the Bayesian evidence analysis, we can see that, for most combination of the data, the GEDA is in a strong favor. Like when Planck, BAO, R19, we have the evidence of high, and all data together, we have the Bayesian, basically the delta evidence of about 6, which is a substantial support for the model. Okay, so the full analysis basically support the data, and current tensions allow us to find models, the statistical better lambda CDM model, but are all tensions resolved? So this is something which is very important here to mention, and it's no. The answer is no, in a sense that even though we have models which are better than lambda CDM, but they are not really resolving all the tensions. And this is a very key point to remember. So I will come back to that a bit later. Few slides about the premodel spectrum. I discussed about dark energy early and late. Now, what would happen if we want to go for beyond the lambda from the power law premodel spectrum? So there have been many groups working on model-independent reconstructions, including our own activity. I started working with the Tarun Suradi in 2003 on the reconstructions. And I think many of you, for example, Raghavan is here. We have paper on that, in mid 2000s on the wavelet analysis. So there were many works going on the reconstruction of the premodal spectrum, and still with the Planck collaboration, also these works have been going on because to see that what flexibility data allows us to have with the form of the premodal spectrum. But one thing which is very important here is that, again, it's the work with Dheeraj and George Smoot already 8-9 years ago, that we showed that, okay, power law is fine, but it doesn't mean that other models are not fine. And this is important for a simple fact that, when you come up with another model which behaves different than the power law, it's not only about this model is better, but the fact is that sometimes the background parameters for these models might be different. So the constraints which we get for these background parameters might be different than the constraints for the background parameters we get from the power law assumption. So in other language, when we have the background parameters in the standard model, baryon density, matter density, Hubble parameter, and tau, and we assume power law, AS and NS, by 2 parameters, then we get, for example, some good constraints on these parameters. But if I just break this assumption and say, like, no, I don't want this assumption for AS and NS, then the constraints we get on these background parameters might be also different. And then, that might be something that we might use to attempt, to see that, okay, if we can come up with a form of premodal spectrum, which can help us with the Hubble tension. So we use or modify the Richardson-Ricci convolution, again, a work which we've been working for many years and is still going on. The latest paper related to this is just appeared this week. And again, going back to this philosophy, in one of our papers a couple of years ago with Tarun and Dheeraj, we could show that if you basically go beyond this assumption of the power law premodal spectrum, indeed, the background parameter contours can enlarge, understandable, but this also gives us another hint that if you can come up with the phenomenological model or theoretical model, which has some special features in its form of the premodal spectrum, you might indeed be possible to end up in some other points in the parameter space. And your X0 may not necessarily be 67 or 68. Of course, these contours are related to the W map at that time, but now with the Planck, these contours are shifted lower. But this is the philosophy which tried to attempt. And in one of our recent works with the Dheeraj and Tarun, we said that, okay, let's do this. Let's assume Hubble parameter to be 73, 74, whatever Schu's collaboration give us. Let's keep omega matter H squared the same because we don't want to play with the the height and depth of the acoustic peaks. But let's now fix this background and then reconstruct the premodal spectrum and see what we get. And this is an interesting results which we get that we have these weird features at the the scales at the larger scales in K. But at the same time, we could see that having this form of premodal spectrum, we are not only resolving the tension with the Hubble tension, because when naturally we get to the Hubble, larger value of H0, let's remember that it's assumed to be there, but also lower value of matter density allow us to have a very good overlap with the results from the shear weak lensing. So there have been similar attempts in this, and I would like to advocate the power of the MRL, because it's a very powerful reconstruction approach, because it allows you to have various features with different amplitudes and different frequencies at different wave numbers. This is something which is really unique for the MRL, and which we try to manipulate here and use. So we try to extend this model with some other works with Ryan, who was my ex-postdoc, and Dheeraj, and then we realized that yes, we may not need some of the features at the high K. At the same time, if you have this packet of features which looks very nice, and then if we can have generate some deformation model, then we can see that where we can have the best reconstruction, and we find that in fact these features can have a very strong support from the data in this work. So there are some issues which we should remember. One of them is that how natural these features are. One would say, okay, you got these features from the reconstruction, but okay, how can you generate such things? So it is very important to come up with some inflationary scenarios that can generate similar features. This is a work which I think Akhil, Dheeraj, Fabio Finelli, myself, we have been working to come up with some form of inflationary potential that, we can come up with similar features. Another thing is that how these features we do with the polarization data. So this is another thing that we have to test, but let's not forget that Planck primarily is a temperature survey. And when we deal with polarization data, we have to consider many issues. And if we want to test or reconstruct features with the polarization data, we should also reconstruct these features considering polarization data. This is another line which I'm working with the Woo Hyun Sun, one of my current postdocs here, and Dheeraj together to do the reconstruction considering all data available. And also we need to consider underlying parameter space and having a more comprehensive iterative approach. And something very interesting is about the lensing. So one of the things that we need to understand is that these features which we derived are very similar to the features we derived in one of our older papers with the Dheeraj and Taran in 2014, which we had a very extensive analysis of the Planck data. And we realized that, if you switch off the lensing, and I said, okay, we don't have any CMB lensing, let's put everything on the features in the premodular spectrum to mimic the effect of the lensing. And we got it such a form. And as you see, there is a very high resemblance between this blue curve and the red curve here. And so this was something that make us to think that feature in the premodular spectrum, CMB lensing and Hubble tension, can there be any connection? And in fact, we found a very interesting connection. And there is a very recent paper by Akhil, Dheeraj, and myself. And I think Akhil today afternoon will talk about this work. So I invite you to listen to Akhil's talk, because I think we found very interesting connection between all these things, including curvature, that might be also helpful to address the Hubble tension. Okay, so current status, problem is open. There are many tensions, many hints for various systematics, which I believe might be really the case. There are many theoretical phenomenological models are proposed to ease the tensions. None is convincing so far. So in our recent work with Dheeraj and Akhil, we might have a very exciting alternative, but we will see how this model works. So it's not possible to resolve all problems with minimal modification of the standard model. So it is important to know that this fact that we have models which are working better than lambda CDM, but none of them are able to ease and release all the tensions, have been working in the favor of the lambda so far. So lambda has been still standing there, says, okay, look, I'm not working better than you guys, but you guys are also not doing perfectly well. So we really need to understand what is really going on and to make sure that there is no tension between the works. So this basically guides us to one of the important attempts, which is about model-independent consistency test between various data, which is important to rule out systematics or obvious systematics between the data. So for example, there was this recent paper, it's published 2021 with Ryan, my postdoc, Gongbo, and some other people. This is the official SDSS paper, which we try to compare in a model-independent way without assuming any model, the Pantone supernova data and SDSS BO data, to see if these two data are consistent with each other. And in fact, we found that they are consistent. But we need to do similar things with different data to make sure that we are not just translating a systematic in some of the data or inconsistency between some of the data to some new physics. So what's the future perspective? Just a few minutes before end of my talk about what's going on. As I said, and I repeatedly said, there is a high possibility for systematics in different data. And by controlling the systematics, maybe we can basically marry things together and things go back to the concordance model. And for this, we need for independent measurements. So it's very important to have some different kind of measurements and to help us to understand that if the current ones are in agreement, or these current ones have any issue or not. And the key issues and key questions remain the same. So these questions have been the same maybe in the last 20 years, power premodular spectrum or lambda dark energy. Maybe it's a good time to address something from the Tanu Padmanabhan here. It was a great unfortunate that PEDE passed away. It was really shocking for any of us. But I have a very amazing memory of PEDE in 2005. In 2005, when the SNLS supernova data comes up and I did my model independent analysis, I got a very well consistency with the lambda, with the cosmological constant, which was killing some of the hope from the previous gold data by Rees group, which there were some hope that there would be some evolving dark energy. At that time, I gave a talk at IUCA, and PEDE was there, and PEDE was saying that, look, I think it is obvious it is lambda, and if one is smart, should try to solve the problem now theoretically. And it was like 17 years ago. And the fact is that yes, yet after 17 years, still lambda is the standard model. And I think PEDE made a great contribution to solve the cosmological constant problem. So I would say that was very visionary, and I always
Arman,
remember that. Yes.
You have 4 minutes left.
Sure, yeah. So it was a very great visionary from PEDE that at that time he tried to shift from data analysis to theory and try to solve one of the most difficult problems, which probably is very difficult to solve. Anyway, so the last few minutes, we need new observations. They are coming. We have these TRGBs, tip of red giant branches, which can basically give us another perspective to have a local measurements. There is a hope that they can go up to 1% measurement of the Hubble parameter. We can have H0 from the strongly lensed systems. There have been holy cow analysis, Cosmogray, which they come up with. You have the strong lens systems, calculating the time delay, basically time delay cosmography. We have been working on this to have a model independent assumptions, and we are at the level of 2 to 3% estimation of the Hubble constant in a model independent way, which is very exciting. It's different from the other measurements. The future perspective for the supernova is crazy, mind-blowing. At the moment we have 1,000 supernova. By the time of the LSST Rubin observatory, we would have tens of thousands of the type 1As, which completely change the shape and the way that we do supernova cosmology. We would have this strong lensing time delay cosmography, which is amazing subject that you have these light curves and you want to separate them and do with few supernova, you can do lots of cosmology because you can observe them just in a matter of a month. And so this is a work that Satadru has been working pretty well in resolving some of these unresolved systems, which can have a huge importance in cosmology, because by having handful of these lens supernova, type 1A supernova, one can get really interesting constraints on the cosmological parameters. From the BAO late universe, the situation would become immensely better. This is what we have at the moment. Let's say that this is the boss, and then in the next couple of years, by end of the decade, we go to the era of the Oichli, W first, and DESI, which allow us to sub-person distant scalar. And from the redshift the space distortion, we can have really good measurement of the growth of a structure, F sigma 8, which again can allow us to distinguish between the modified gravity models. We have gravitational wave and standard sirens coming to the picture at the moment, not well, but with the having more sensitive detections. There were many talks yesterday. We can basically have a less than 2% uncertainty on the Hubble constant using the gravitational wave. And from the early universe side, we can have the CMB4, hopefully, which allow us again to distinguish between many models which are not distinguishable. In this direction, I would say that another important perspective is that to shift from the 2D to 3D, that we can have luscious structure to test early universe scenario. This is one line that my group has been pretty active to do, to come up with some going beyond the 2-point correlation function, and then trying to see that if we can use the 3D information luscious structure to distinguish between the early universe scenarios. So my last 2 slides. We have cosmology, we have systematics, and we have assumptions, which we have here. So with the high quality of the data, the role of systematics becoming more and more prominent. Let's not forget that when you have a high precision, then the bias or accuracy become more important. So when the precision is low, it's okay to have little bias or uncertainties in the accuracy. But when the precision is high, little accuracy matters. So this is something which we should really be careful. So attempting understanding systematics become much more important. So at the moment, a standard model fits different data pretty well individually, but when we have different combination, then things become a bit messy. This allows us to have, good competitive alternatives. We should look for them from the early universe side to the late universe side, and but we should see. So it's good for theorists to work, but we should be careful to understand the systematics. So tensions are not resolved with minimal extension, which hints to systematics. We might have systematics in some of the data, not only in one of the data. And we can have also a combination. We might need new physics as well as systematic. So the problem is really, really open. So in the 2020s, at the moment, we are working on the snow mass white papers to come up with what is going on in this decade. So the first target probably would be at the pillars of the standard model, lambda dark energy probability model spectrum. And in this decade, by DESI, Euclid, LSSTW first, I do not say SKA because maybe not in this decade, it's for the next. We will make it much more clear that what would be the situation for the standard model, and if we need to go beyond that or not. So hopefully we need, because if we don't, then probably it will be very difficult to get funding from the agencies for reducing the uncertainties. So let's see what would happen. Okay, thank you very much.
Yeah, thank you very much, Arman, for such a nice presentation and talk, and informative as well. So it's time for questions. So anyone with questions can please unmute and ask.
Sumati, go ahead, please.
Yes, thanks for a very nice talk. I was particularly intrigued by, so this BAO data, the tensions have been also of interest to people who work on causal set theory, which accommodates a fluctuating cosmological constant. And these were ideas due to Raphael Sorkin from a very long time ago. And so there's this work, more recent work, discussing the BAO tension by Afshordi, Sorkin, and Zwane, which I'm not sure whether you're aware of, but it's actually talking about how a fluctuating or an ever-present lambda does as well as CMB, if not better, in certain tests. And so the idea is essentially that of that from an underlying discrete, so it's a stochastic cosmological constant. Now, one of the things, so you talked about omega lambda, which is basically varying over time, which is so something that is small in the past and becomes larger now. What I wanted to ask you is, how do you fit that into the standard how do you fit that into general relativity? What sources this kind of fluctuating lambda? Because that's one of the challenges, not having a constant lambda. How do you fit it into GR?
Okay, so first of all, thanks for comments. For the PEDE, as the name is a phenomenological model. So, to theorize that, to come up with the theory which come up with such an emergence, that's not easy. I have one work on that with some of my collaborators, Nima Khosravi, and he's a student, which we try to use the critical phenomena that's as something that can trigger a phenomena to comes up. But yeah, the model is phenomenological, and we assume GR. So we are not going beyond GR. GR is there, and from the gravity side, and so the perturbations, everything, considering that, and but from the theory side, of course, we need to find out how things going on. But I personally believe in phenomenology first and then theory. So first understanding how data suggests, and then trying to theorize that. But the model practically works in this way that we need to trigger it somehow. For example, one of my very raw idea, very beginning, was that, okay, if I can trigger something by the growth of structure, let's say when the matter fluctuation basically, cross some particular extent, then that basically trigger a phenomena and dark energy basically emerges. But as I said, this is a phenomenological model, and if a theory can come up with a similar behavior, that would be very interesting.
Yeah, so I've just put in the reference here in case that's of interest to you, because sure, it's in particular analyzes the BAO as sort of possible indication of a fluctuating lambda, and so that might be of interest.
But okay, fine, but let's fluctuating lambda is not yet very much supported by the data. Okay, so this is another thing. There are many works in the literature which, okay, that might be a possibility, but it's not something that we know that phenomenologically fluctuating lambda works better than the other models.
Yeah, I don't think we have much time, but maybe one quick question from Sriram or Raghav.
No, Raghavendra, please go ahead with your question.
Okay, thanks. I just wanted to ask, you briefly mentioned about the features in polarizations should be accounted for separately. I thought when you code these improvements, aren't they already accounted for, or are you suggesting that one has to look separately at the features, the CL corresponding to the polarization modes?
Okay, thanks for your questions. When we did the reconstruction, we just considered the temperature data. So the reconstruction is done only on the temperature data. The likelihood analysis, in some cases we did with the polarization, and in some cases we didn't. But let's not forget, the power of the temperature data is substantially stronger than the power of the polarization data. So sometimes you might get a huge improvement with the temperature data, but still you may get worse polarization likelihood than the power law. But since your improvement in the temperature is substantially higher, you might in overall get a better fit. But in the reconstruction, we didn't use the polarization data. So that is something that we are trying to do now.
Okay, thanks.
Okay, thank you, Raghavendra, for your question, and thanks to Arman once again for such a nice presentation.